Hello, 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 and welcome back to another episode of Kerbal Space Programming. Kevin here, and we are on board the KSS at the moment. Well, I say on board. This is still, thus far, a completely unmanned capsule, and I need to get some better lighting up here. But we are, one of the things that we need to figure out for our plan to land on Minimus and come back is how to actually transfer from a low Kerbal orbit to an intercept with Minimus. Now, with the moon, this is relatively easy, making a few assumptions. If you were in a circular orbit and you want to transfer up to a different circular orbit, well, then that's just a home and transfer. And we've done that in the past. The problem with Minimus is that there's an inclination change involved. If we look here, yeah, it's going up and down around our orbit. And this one is circular, but we want to, what if it weren't? And also, what if our orbit is not completely circular? In fact, this is pretty darn close, but it's not. Let's see, we've got 257 and 201. Okay, so not particularly circular there. Now, in all likelihood, if we did calculate something, it'd be pretty close, but we want to have a transfer that actually seems to work. And we also want, ideally, to have some sort of function that gets us not just to Minimus, but is able to transfer back, and that's a little bit more complicated. So the math for figuring out these complicated orbits is rather tricky, but as you know, because we're computer people, we can think about, well, all we're trying to do is create a maneuver node, right? We're trying to create something that will eventually intercept us with Minimus. That is not one. If we think about what we do when we're playing this game manually, that's probably, we get there-ish. Yeah, that's going to miss. That's fine. We'll go ahead and maneuver this around, see if we can get an encounter. See, this is the part of the thing is that I'm not particularly good at getting these encounters even manually. But we look at how this is happening. What are we actually able to adjust with this maneuver node? Well, we're able to adjust when it is. We're able to, wait, did that? No, that just put us into space. Okay. We're able to adjust the normal and anti-normal. We're able to adjust the radial and the anti-radial, all of that fun stuff. And then we're able to adjust the prograde and retrograde point. So there are three different variables regarding the node itself. And then there's one that involves when we actually run the maneuver. And those are the only three things that vary, no matter what sort of maneuver we're doing, whether we're trying to say, come back to Kerbal, or we're saying get out to Minimus with some sort of periapsis, or encounter some other thing or do a rendezvous, anything. It all comes down to just figuring out the right four values, this prograde, this normal, this radial, and the actual time to execute the burn. And of course, if we think about this, well, that's great because we've already applied some strategies for figuring out combinations of values to get us a good output, right? We're just trying to optimize these four input values so that we get the output that we want. So let's think about exactly how we can do this. The initial way, and if we think about how I would be doing this if I were to spend time trying to actually find the maneuver node, I'd probably just do an inclination change first and then figure it out. But if we think about how this works, I'd go ahead and tweak one and go, is that closer? Yeah, okay, good. If I go here, nope, that's worse. So I don't do that. I go, okay, well, this is way above, so maybe I'll try adjusting this, try and bring the thing down, up, now that's worse. And you make these incremental adjustments and you evaluate that the output is better or worse. And so this seems like something that we can do programmatically rather than having to figure out all of the math for all of the various different types of problems that we might have to solve regarding maneuver nodes. So let's try and do that. So what we're actually talking about is called hill climbing, which, as it says here, is you start with an arbitrary solution and then you attempt to find a better one by incrementally changing a single part of the solution. So we've got four variables and we're just going to try and tweak some of them, the way that we want. Now, this is kind of an example. If we look at this graph over here on the right, it's got this hill, and we would, if we're at some random point, we'd look and say, all right, well, if I go, plus y by 1, or I guess minus y, I don't know what these axes are, but if I go 1 in this direction, hey, look, I'm a little bit taller, so I'm going to go ahead and do that. And then you just do that over and over until you're like, hey, everybody around me is worse, so I must be the best. It's high school for computer science. Now, one of the problems, and this is the big one here, and ignore, I don't know what this is doing. But if we look here, here is a path that has 2 humps. This has 2 what's called local maxima. And that means that there is a solution that looks like the best if we're nearsighted. If we get to the top of this hill and we look around, then we discover, hey, any move that I can make right now is worse. And therefore, I must be the best, I'm done. When in reality, we're just at the top of this little peak, and really we want to get ourselves over to here. But of course, we have an algorithm that we know actually can solve these types of problems. It just may not do it particularly fast. We've done the genetic algorithm approach, which you remember is basically generate a whole bunch of solutions. So it would plop random things down on this example map, and we would have them evaluate and then would say, which are the best ones? And then would say, you're more likely to make it down into the next generation. So if there's one that ends up somewhere on this hill, and the rest of them all end up being here, it's more likely that this one is going to be a parent to the next generation. And we slowly creep ourselves up. But there's also randomness, there's mutation that's introduced into those values such that they can sometimes jump around. So that even though they start to converge on a single point, they may just randomly stumble across. So if everybody's on this little mountain, randomly some guy could end up over here and he could go, hey, we should hang out over here. The water's fine. And as long as the randomness, the fuzziness factor, the mutation is enough, then we can go ahead and make that leap and we won't get stuck here in local maxima. So the big question that we have to ask ourselves is whether or not local maxima exist for maneuvers. Because if just doing hill climbing seems like it should be faster. We take one solution and go, let's look at all the tweaks we can make and see if one of them is a little bit better. If we're doing genetic algorithms, then we have to have like 100 different attempts and do this crossing and mutation and all of this stuff. It's an awful lot more work and it's going to take a lot more time. And it theoretically could take an infinitely long amount of time to find the right solution or a good enough solution. It's not something that's predictable. Or even if we say, give me the same maneuver node, if we tell it to search again for the exact same thing, it might take a different amount of time. Just because it's so much dependent on randomness and randomly generated crossover and mutation. So the question is, can we get away with naive hill climbing, or do we need something that's going to avoid that local maxima problem? Is it going to get stuck on a solution that is a little bit better than every tweak that it could make, but isn't the right solution? And I think I can come up with one, because we only need one to decide, well, that's not going to work. And my fear is, let's imagine that we are here and that Minmus is there and that the moon is like right there, right in our path or something. It's entirely possible that we could end up in a situation where we encounter the moon and the moon's gravity pulls us into the sphere of influence of Minmus. But if we're trying to find a good encounter with Minmus, one that gets our periapsis to what we want it to be, it could be that there's some sort of gravity well interaction that means that we could get stuck saying, hey, I just barely got to Minmus, but if I try and get down to the right altitude around Minmus, then I end up crashing into the moon. So this is the best solution I can come up with. Or if it just say, I'm just going to wait in orbit, then it could go direct and it could be entirely fine. So that to me seems like one of those little peaks where it could get stuck thinking this is the best solution. And so naive hill climbing is not exactly going to work. Alrighty, so it looks like we're going to have to go with the genetic algorithm approach. So let's look at some of the code. I've gone through and sort of rewritten a bunch of the older libraries that we had. One of them, you may remember, was the float library, and this just converts floating point numbers, so numbers that can have decimal points, into strings of ones and zeros, because those are much easier for us to manipulate in genetic algorithm land. And all that is now it's encapsulated in this float variable, and we could say things like float to float and give it this series of things and get out the number. So this just lets us pack things away into something that's going to be easy for the genetic algorithm to play with. This code is complicated and messy, so we won't really go over it, but it lets us go from one to the other, and that's all that does. Next, we've got the genetics library. Now, the last time we did this, it was to get ourselves an awesome launch, and that was great, but it was very complicated because we needed it actually to be able to revert to launch and persist stuff. That's not necessarily the case with all of this. So let's review kind of what the genetic algorithm does. So this prepare is just setting some internal stuff, but what it's going to do is it's going to take a starting population, which we're going to pass in here. It's going to evaluate the starting population, so it's going to give them all scores. It's going to select the ones that had good scores. It's going to select a random set favoring those with the best scores. It's going to crossbreed those parents. So it's going to take, the first half of parent A and the second half of parent B, and then the first half of parent B and the second set of parent A, and say those are the two new children. It's going to mutate them, so it may randomly change a 1 to a 0 or a 0 to a 1, and then it's going to evaluate them again, and it's going to do that until there's some reason for us to be done. Now, of course, this file is rather long. We've got to prepare stuff. It's tracking the generation. It's tracking the best fitness. It's tracking the best candidate. It's got this evaluate stuff that's relying on a bunch of stuff. Now, the reason that this has been rewritten is because we're now able to do stuff with function delegates that we weren't able to do before. So you can pass in, you can say GA seek, and we can pass in a lexicon with various things like the population, which would be a list of something, and the fitness function. So we can say, this is the way you give me a chromosome and I will tell you what it scores at. And then this genetic algorithm could just worry about trying to do the genetic algorithm part, and we can pass it a fitness function that fits the solution that we're looking for. So next we have the transfer. Let me close that up. Next we have the transfer library. This transfer library, this is the thing that we want to actually do. All right, so those were two sort of helper libraries that we need to help sort our problem. We've got a transfer library that's going to seek a good maneuver. And here is the function that it's doing. So we've got some constants up here. That's fine. We've got this function seek, and it's going to take a target body, and it's going to take a target periapsis. And it's going to say set the seek time to time seconds plus maneuver lead time. So we don't want to say, hey, I maybe found a node, maneuver node 2 seconds away from now, because it could take us a long time to figure out that that's a good solution or not. So we're going to say, don't try and plan any maneuver nodes that are less than 10 minutes from now, because we maybe need time to evaluate them. And here we say we're actually declaring that lexicon that describes our genetic algorithm stuff. So we give it a starting population, we give it a fitness function, and we're giving it a terminate function. We say this is how you know when you're good enough, so you can be done. So then what we're going to do is we're going to decode the best solution that the genetic algorithm comes up with. And that's all that we're doing. We're just running this genetic algorithm until we're done. And of course, the actual details of how this works are in these interior functions. We've got starting population, which is just going to create a whole bunch of random bit strings, which is fine. So it's just going to take a random number between 0 and 1, or in these cases, -1 and 1, and turn them into bit strings. So it's going to say these are the populations. We're going to create 50 of those, and we're going to return that as the population. So that's our starting population that we're going to give the genetic algorithm. Now we have the fitness function, and here is where things are tricky. So we take in a chromosome, we have to give it back a score. So the chromosome is a series of 0s and 1s, and our bit string is just, our chromosome is just 4 values. So what we're going to do is we're going to decode our chromosomes. We're going to say, take this bit string and give me a maneuver node that associates with that. We'll say, okay, we're going to give ourselves some penalties if we didn't get the transfer, if our periapsis is wrong, and if we spent a lot of delta V. So we'll go ahead and add the maneuver node to our flight plan, and we're going to assign these values. So we'll say the delta V penalty is 1 minus the difference between the difference between spending a lot of delta V and no delta V. If we actually got into the sphere of influence where we were trying to go, then we'll say your transfer penalty is 0. And your periapsis penalty is 1 minus whatever the difference is between the next orbit's periapsis and the target periapsis. If we didn't get into the correct SOI, then we're going to try and figure out, okay, well, where will we be if we run this maneuver node at the apoapsis? We'll say, okay, so the maneuver apoapsis time is the current time plus the time to the next node plus half of that next node's orbit. That's an assumption. It may not be true. But it's the best guess that we have at the moment. We're going to say, okay, well, if we ended up flying out of the system, then we're going to use that apoapsis, because we shouldn't be judging that as the right. We want to make sure that we're penalizing this. We'll say, okay, let's find where our position is and our target's position is at that particular time. Now, this assumes that maneuver nodes do get executed. And we'll set the transfer penalty to the difference between those positions. We want to say, at apoapsis, how far were we away from min-miss? Was it a lot? Was it not a lot? That's the penalty. If we were at min-miss, then our penalty should be 0. Then our score is just going to be these penalties times the transfer penalty weights, though, because, yeah, we've got 1 over 1 plus because they're penalties and not scores. And I've added a little weight here so we can actually watch this in action, and then we return the score. So this is a very complicated fitness function, but the idea is that we want to track these 3 values. We want to determine how good of a maneuver node this is. 1, did it get to min-miss? 2, is the periapsis of the min-miss orbit close? And 3, did it use a lot of delta V to get there? Because we don't want to spend, we don't want to necessarily spend a ton of delta V if there's a better option there. Then we've got the decode function, which just takes out the time for the maneuver node, the radial, the normal, the prograde, and we have to play around with those numbers a little bit to get them between 1 and -1. And then we go ahead and say, all right, so we're going to say that we're creating a maneuver node based on those times, basically. And we've also capped this, so rather than having the prograde number be the actual number for delta V, we're going to say you should be a percent. You should be somewhere between 0 and 1 or -1 and 0 and multiply by some maximum axis delta V. So we're never saying, hey, I think we should try 30,000 delta V in this direction. We're just going to say you're scaling up this number, which I believe we set to like 5,000. Then we've got the Gaussian function, which we've done in the past. It's confusing, but it's getting us a nice little sloped function so that a bad value is still a little bit better than a worse value. Okay, so now we have the maneuver terminate function, which is just deciding whether or not we should be done. And I have this actually commented out here because I don't know what the right time is for us to be done. What we're doing, though, is we're also adding the maneuver node just so we can look at what the result is, and it's going to tell us what the score is, and it's going to tell us what the delta V is of those options. So there's our transfer library. Now, the transfer test, we're going to run these 3 helper scripts. We've got run float, run genetics, and run transfer, and then we're going to say, transfer, all right, you need to seek a maneuver node, and in actual use would say something like set solution to transfer, but we don't need to worry about that now because we're just trying to test this out. We're going to say transfer, seek a maneuver node that is going to get us to min-miss with a periapsis of 20,000 kilometers. So let's go ahead and jump over to the KSS and ask them to run our script for us and see how it goes. And run transfer test. And yes, I'm aware this is very small. We're not going to be actually looking at any information off of here. I'm just going ahead and running the script itself. Oh, there we go. Alrighty, it is running. And it is taking some options. We can see most of these seem to be relatively small. There are a couple that are shooting out vastly into the solar system, and it's assigning scores for these as it goes along. We see most of them are very, very, very small. And once it gets through those 50, then it will briefly pause on the best one and let us know what the delta V was, at least for the best one that it found according to the fitness function that we wrote. So, yeah, a lot of these where it just kind of stays mostly exactly where it is. Okay, there's the best option that it found. It got itself an orbit to like out there. And somehow it ended up taking 1767 delta V to do it. I don't know what it did. Did it find a retrograde maneuver? Like, did it completely cancel out? I don't know. I don't know what it's doing, but all right. And at this point, it is now trying to combine those, or it's selecting the best of those 50, and then it's combining them together to create the children, and then it's doing the mutation, and so it's pausing. Okay, so it's yeah. Some of them are going there because we've got 50. There's more of an opportunity for diversity to be maintained. So it's less likely that things are going to converge on one solution right away. You'll still have a bunch that go, hey, that whole maneuver where you were like, hey, let's go that way. That was a good idea. But you're going to get a bunch of randomness still hanging out there as well. All right. Yeah, see, these scores are a little bit misleading because some of these are to an exponent. All right, that's still the best one that it found. So it's not showing the best. Oh, and it goes down like that. That is not a good best. Well, I guess if you're going out there, you're looking around, that's not terrible. It is showing the best one that it has found thus far, not necessarily the best one of the generation. So it's going to go ahead and track these, and hopefully things get a little bit better. I'm going to go ahead and zoom out. Well, once these things start, I'm going to go ahead and zoom out so we can see some of the candidate solutions that it comes up with. And all it's doing is it's picking values for these four. If we look, see. Yep, see, look. It's finding a whole bunch of these that it thinks maybe this will work. It's just setting those four values. The when do we run a maneuver? How much delta V do we put in on the prograde direction? How much delta V do we put in on the radial direction? How much do we put in on the normal direction? And yeah, even though, it's throwing a lot of stuff out into deep space. They are all coming back with these, negative 0.5 exponents. So they shouldn't be super heavy competitors. What is that one? That's okay. So for reference, it should probably take about 1,000 meters per second of delta V to transfer to minimus, around there. This right now, its best solution thinks that it should take 5,000 and not even get there. So, all right. It is going to take many generations, though, for us to find the optimal solution. So I'm going to go ahead and cut away, and then we will come back. Oh, look at that. Already generation 4. So that one actually did find an encounter. It decided that the best thing to do is pretty much go in like a straight line path to fly by minimus, and of course, on the wrong side. So nothing in our scores penalizes a retrograde orbit, right? We just say that the periapsis has to be 20,000, or at least you want to do that if you want a high score. But yeah, so we probably want to build something into our fitness function that gives us a better score. And now you see that some of these, yeah, see it picked up on that again. It tried to, yep, got a bunch of these that are trying to just go ahead and make a straight line path pretty much right by minimus. But of course, it's spending a lot of delta V to do that, spending 5,000 meters per second of delta V for basically just a really fast fly past, which is not probably the solution that we would want it to come up with. But still, after only 4 generations, it's converging on that. So hopefully maybe from there, it can go ahead and come up with a better solution. So yeah, it still thinks that's the best one. 5,153 meters per second at delta V. That is an expensive transfer, to say nothing about having to cancel the velocity once we get home. And jumping back in here around generation 28 or so, we've been running for quite some time. And it seems to pretty much favor this flyby, which you see, it's not showing a particularly long amount of time to kind of illustrate, but it is a very quick flyby. Not necessarily the best of things. See, okay, delta V is now dropped down to 5152 from the 5153 that it had been before. All right, so that was generation 27. And yeah, so here we see a case where the genetic algorithm does not seem to be finding a good solution. It seems to find some solution. What we've effectively done is created our own little local optima by the way that we've weighted the actual penalties. So I'm imagining what it's doing is saying that it is more important that its periapsis is correct than it is that it saves fuel. And so it's stuck in this position where, theoretically, if you ran this for an infinitely long amount of time, it would eventually find a great solution with a reasonable delta V, but it ends up getting stuck here. What we need to be able to do is trying to find some sort of fitness function by which we can say, this is a good maneuver, this is a bad maneuver, and it has to be such that if we have, it's pretty easy. If we transfer, then we can look and say, all right, well, where's the periapsis? And I guess we could also look and see how far out the escape is, maybe, right? I guess we could wait on that. And we could say, okay, so if you get there and your periapsis is good, then you should try and make sure that your escape is not too crazy. Then you should also try and make sure you're not using a bunch of delta V. But what happens if we have something that doesn't get there at all? Well, then our whole formula for figuring out whether it's good maneuver or not doesn't work because we didn't reach there. We can't compare the periapsis. And so we've got this function where we need to have a way for genetic algorithms to work well. You need to have some sort of function that can say, this is an absolutely terrible option. It doesn't work in the slightest, but compared to another terrible option, it is a tiny little bit better, because that's the way that you get the feedback in such that it ends up advancing. And so now it's really kind of trapped in this solution of let's just go straight there. So there we go. Genetic algorithms do not seem to work too well for solving this problem, or at least I haven't been able to come up with a fitness function that works. If you have a solution that could perhaps work a little bit better, let me know, or go ahead and take a look at the source code. There's a link, as always, in the comments. All right, so it's improving according to its own stats. The delta V went up, but I guess maybe its periapsis got closer. So if you've got a solution for a fitness function that maybe is more appropriate that we can go ahead and try out, let me know in the comments, because I'm stymied. But I will see you again next week. Cheers.